All right. So as I promised that I'm going to post something on theory of work, energy, and power. So here, this is for that. Okay. So this chapter is about work, energy, and power. Okay. So the first work. So in our everyday life, we do work, lot of work, right? But not all of our everyday work is work in our physics. For example, doing homework, you probably do a lot of work, but it is not a work in physics. Okay, classwork is also not work in physics. Okay, so interesting. So here we are going to learn what is actually physics, what is actually work in physics. Okay, so scientific definition of work. So first of all, we use W, capital W for work. Okay, so capital W for work. Do not confuse between this and work. So this is weight or the gravitational force. Okay, small w is for gravitational force and capital W is for work. Okay, do not confuse between these two. So that's the first caution. All right, so to understand work, we need to understand force, we need to understand displacement. And we already understand force and displacement, right? We learn force in chapter 4 and displacement in chapter 2. So we are almost expert on that. So now we can define work. Okay. So work is defined as by this equation. W equal to FD cosine theta. So to understand this, let's say we have a box, okay, and we are applying a force on this. And because of this force, the object moves here. This box moves here. So that means it changes position, and changes position means there is a displacement d, right? We apply a force, and because of this force there is a displacement, right? So now we can say that we did work on this object. So the the definition of work done is when we apply some force. Okay, so that means we need to apply force, and because of that force, if the object moves, okay, that means if there is some displacement, okay, then we can say that that force does some work on this object. So F is force, D is displacement. But what is theta? Theta is the angle between these two. So in this case, force is in this direction, displacement is in this direction, right? Both are in the same direction. So that means theta here is actually equal to 0. Okay, in this case, cosine theta equal to cosine 0 degree. Okay, and that is equal to 1. But sometime, let's say we have this object and we apply force in this direction. And because of this force, let's say the object moves to this position. Okay, so the displacement is this, force is this, and here you see that if we draw a line parallel to the displacement, we get this angle. So angle between the force and a parallel line to the displacement is theta. Okay, so theta is actually, I mean, in general, when you define define the work done, we need this angle, right? So this is very special case. Okay, when both are in the same direction, but it is a very simple case when both are in the same direction. Okay, in general, it there may be some angle between theta, between F, the force, and the displacement, like this. Okay, so that's why in general, the general definition of work done is this: FD cosine theta. Okay, now this equation is valid only when F is constant. Mm, Remember that you can use this equation when F is constant, a constant amount of force applied to the object. Okay, if the force is variable force, there is a different story. Okay, we will see at some point in the chapter. Okay, all right. Now This is our definition. W equal to FD cosine theta. F is a vector, displacement is also a vector, but W is a scalar quantity. Okay, strange, right? You know, we get a scalar from two vector quantities. Okay, this may be strange, but actually, if you know the vector calculus, in vector calculus, we call a dot product or scalar product. When you do a scalar product of two vector, you actually end up with a scalar. Okay, so here I'm not going to teach you the vector calculus, but because of this vector calculus rule, although f and d both are vector quantity, the product w is a scalar quantity. Okay, now all the scalar you learned so far, okay, are always positive. Okay, so for example, the distance is always positive, right? Speed, always positive. Mass, always positive, right? So this is the first scalar in this course we are learning, which can be positive and negative as well as zero. Okay, why? It actually depends on theta. This cosine theta. Cosine theta can be positive, can be negative, and zero, right? So that's why, the work can be positive, negative, and zero. Let's see when it is positive, when it is negative, when it is zero. Okay. So if theta is in between 0 degree and 90 degree, okay, then cosine theta is positive. Okay, so if cosine theta positive, W is also positive. So this is one. Okay, some example. When you push, pull, these are basically common example of positive work. Okay, theta, if theta is exactly 90 degree, cosine 90 degree is equal to 0. So that means work done is equal to 0 when the force and displacement are perpendicular to each other. Okay, some example, for example, the normal force. Okay, normal force is perpendicular to the displacement. We'll see in the next page. Okay, centripetal force. Okay, so there does no work. Okay, so some example of zero work. And then the last one, if theta is in between 90 degree and 180 degree, cosine theta as well as work done is negative. Okay, example, kinetic friction. You know, kinetic friction is always opposite to the direction of motion. So that means the angle between the force and displacement is 180 degree. Okay, so that's why kinetic friction does negative work. Okay, all right, so let's see some other example and the picture of those work in the next page. Before I do that, the standard international unit, okay, SI unit. So SI unit is joule and J is for joule. Okay, 1 joule is equal to 1 Newton meter. Why? Because force is measured in Newton, displacement is measured in meter. So 1 joule is actually equal to 1 Newton meter. Okay. All right. Now look at these pictures. Okay. So here, the first one, this one. So the person is applying force in this direction, right? And because of this, object is moving in this direction, right? And this angle is less than 90 degree. So pushing here, you see, at less than 90 degree is positive work. Here you see, holding a suitcase or a bag and moving upward in the stair. Okay, so you know that when you hold something, you actually, you know, apply force against gravity. Gravity is downward. You know, if there is no support, it will go downward because gravity, the earth pulls everything downward. So no, you have to apply force in the opposite direction of the gravity. That's how you can hold something. Okay, so you are applying here force in the upward direction, and you are moving in this direction, right? So the displacement is this one, force is this one. So angle here, theta, is again less than 90 degree. So this is a positive work. Surprisingly, this one. So, you know, exactly same thing. Instead of walking in the stair, you are walking in the horizontal plane. Now, your force is again upward, you know, force against gravity, right? But the displacement is perpendicular, right? So this angle is 90 degree. So that means you don't, this person does no work here on this bag. So again here, applying force in the upward direction to hold this bag, but she's not moving. That means displacement is equal to zero, right? Although she's holding, let's say, some important document, okay, you know, still she doesn't do any work here because displacement is equal to zero, right? And then here you see the centripetal force. So centripetal force is always toward the center, right? Toward the center. And then direction of motion is tangent. You know, this red line. The red and green always perpendicular to each other. No matter where the car is in this circular path, in any circular track, always the force, the centripetal force, and the direction of motion perpendicular to each other. And perpendicular to each other means theta equal to 90 degree and cosine 90 degree is equal to 0, and work done then is equal to 0, right? So centripetal force does no work. Gravity, you know, gravity sometimes does work, sometimes not. Okay, so for example, here gravity does some work, here it doesn't do any work. Okay, so you know the gravity will be in the downward direction, so here in this case, and then displacement is this, they make perpendicular to each other, right? They make an angle perpendicular to each other. So work done here for the gravity is also 0. Here gravity is downward, but then here you see this angle is not 90 degree, but it is greater than 90 degrees. So gravity in this case does negative work. Okay, you know, we will be solving some problem and you will see that, and it will probably make more sense than, you know, these. All right, so here the object is sliding downward. So the displacement is in this direction. And you know that kinetic friction is always opposite to the direction of motion. So kinetic friction is in this direction, right? So displacement is in this direction, kinetic friction is in this direction. So that means here, this angle is 190 degree, sorry, 180 degree, right? 180 degree. So that means this is here. This is this category, right? And cosine 180 degree is actually negative one, exactly negative one. So kinetic friction does negative work. Okay. All right. Normal force. You know, the normal force is this one, right? So here you see the normal force and the displacement perpendicular to each other, right? So normal force does negative work. Sorry, zero work, no work. Kinetic friction does negative work. Normal force does no work. Okay. All right. All right. Now the net work done. You know that we already know that when we have an object, several force can act on a single object, right? So then, you know, what is the net work done? Net work done is basically the sum of all the work done. Okay, so let's draw a situation and then discuss that. All right, so let's say we have a box. Okay, so let's say we have this box and it is moving forward. So that means someone, let's say, push a force. So this is applied force, and and let's say it moves from here to here. So this is the displacement. Okay, so we have applied force. We must have gravity, right? Mg. We must have normal force because it is on some surface. Okay, and if there is a friction, there will be friction, and this will be in this direction, right? Now, some of the force may not do any work if they are perpendicular, right? Then cosine theta equal to cosine 90 degree, which is equal to 0. So, for example, in this case, um, gravity does no work, normal force does no work. But you know that applied force does some work, applied force does positive work, and friction does negative work, right? And so we have to calculate the work done individually for each of these forces. Okay, and then the net work done is sum of what we get here. So let's say you get plus 90 newton here, and let's say you get 70 newton, negative 70 newton here. So when you add them together, you get plus 20 newton. So the net work done here is plus 20 newton. Okay, all right. So it's basically similar to the superposition principle. When we have more than one force, we have to add them together using the vector. But work done is not a vector, so it basically adding them together. Okay, but we have to be very careful of using the cosine theta. Thus work done can be positive, negative. So for example, here in the problem I just erased. Okay, we have positive work by the by the applied force and negative work by the kinetic friction. Okay, so you know that if you messed up with the sign, then you will be ending up with some incorrect final answer. So we have to be very careful when we add them together. We have to keep track of the sign. Okay, all right. Next is energy. Okay, all right. So in this course and physics 2, we'll be discussing different type of energy. Okay, so we have many types of energy, the kinetic energy, potential energy, electric energy, thermal energy, heat energy. Okay, so a lot of this you will be learning in physics course itself, and there may be some other course you also learn about energy. Okay, so what is the simple definition of energy? Okay, I mean, because we have different type of energy, of course different type of energy has different definition. So we don't give you a unified definition for energy. Okay, but in simple word, energy is actually the ability of doing work. If you have energy, you can do work. Okay, but in this chapter our focus will be on mechanical energy. Okay, and what are the mechanical energy? Mechanical energy, actually kinetic energy and potential energy gives us the mechanical energy. So the definition of the mechanical energy, here you see that sum of kinetic energy and potential energy. Okay, K is the kinetic energy and PE is the potential energy. So when I say mechanical energy, it's basically sum of the two energies, kinetic and potential. Okay, all right. Now, before I go to talk about the kinetic energy, remember that the Energy is a scalar quantity similar to work. And here in this section, you are going to see how work and energy are related. Okay, so energy and work are related. And as I already mentioned in one statement, that energy is the ability of doing work. We already learned work is a scalar quantity, so energy is also a scalar quantity. Okay, and surprisingly, they share the same standard international unit. So that means the joule J is also the standard international unit for energy. Okay, all right. So yeah, joule. All right. Now kinetic energy. Okay, so kinetic means actually in motion. Okay, so you know that kinetic friction, right? Kinetic friction means the object is in motion. The same thing here. Kinetic energy is the energy of motion. When the object is moving, then we have kinetic friction. Sorry, kinetic energy, right? And the definition of kinetic energy is this one: half mv square. M is the mass and v is the velocity. Okay, or speed, basically the magnitude of the velocity. Half mv square. So you know that if v equal to 0, then kinetic energy equal to 0, right? When there is no motion, when there is no speed, there is no kinetic energy. Okay, so remember this. And that's why its name is kinetic. Kinetic is the energy of motion. Okay, now let's talk about the work energy principle. Okay, so work energy principle tells us that how work and kinetic energy are related to each other. Okay, the work energy principle is this equation: net work done is equal to change in kinetic energy if there is no other form of energy, changes. You know, if there is only one kinetic energy changes, okay, then the net work done is equal to change in kinetic energy. Okay, a simple let's look a simple simulation. Okay, here this one. So here we have this object, okay, and we apply a force on this object, right? If we apply force, you know, that means we do work. Neglect and forget about the thermal energy, I mean the, you know, the friction. So let's say there is no friction here, so that means when you apply force here, okay, you do some work. If it moves, right, it looks like when you apply this force, it moves from here to here. Okay, so that means you do work, right? Definition of work done is F D cosine theta, right? So here you have F, you have D, you have cosine theta. Cosine theta here is actually 0 degree, right? Both are in the same direction. So it is 0 degree, cosine 0 degree equal to 1, right? Let's see what is actually going on here. Okay, so here. So now, right now, it is at 0 meter. We apply force. So this force is equal to 20 Newton. When you push this, you know, this is a constant force. Um, um, where you apply this force here, and because of this force, you do this much work. Right? So here you see that you apply this force. Because of this force, it moves from here to here. Okay? So, you know, we can calculate the work done, net work done, right? Here, if I write, so this will be W equal to F is 20 Newton, okay, D is 35.1 meter, okay, and cosine theta is cosine 0 degree, right? Because both the force, so this is the force, This is the displacement. Both are in the same direction, and cosine 0 degree equal to 1. And if you do this math, it will be approximately 702 joule. So the work done, the definition we just learned, okay, by applying here, we see that work done is equal to 702 joule. Okay. Now look at the speed. Speed is speed information. At the beginning, here, the object was at rest, right? When we apply this force, it starts moving, right? It gains speed, right? So here you see that when it is here, it gains speed equal to 26.5 meter per second, right? So that means the kinetic energy changes. So here we have kinetic energy that was equal to 0 because the speed was equal to 0. It was at rest, right? Initially it was at rest. So that means the kinetic energy here, it was equal to 0, and as it is moving, the kinetic energy increases because here you see the speed is equal to 26.5 meter per second. So that means because of this work, kinetic energy changes. Okay, kinetic energy changes, and this kinetic energy, if you use the kinetic energy equation, so here the kinetic energy equal to 0. So the initial kinetic energy is equal to 0 because V equal to 0. Remember that kinetic energy is equal to half mv square, right? So this is the initial kinetic energy. Final kinetic energy is half mv square final. Okay, so half m is what? M is 2 kilogram, 2, and we have bf is this one. So 26.5 square. So these two cancel out. 26.5 square is actually equal to 702 joule. Right? So you see that net work done is equal to kinetic energy, change in kinetic energy. Change in kinetic energy is final kinetic energy minus initial kinetic energy, which is exactly equal to 702. Right? 702 minus 0 is 702. So this proves that the net work done is actually equal to the change in kinetic energy if there is no other form of energy changes. Okay. Okay. So let's do it again. Okay. So here you see the speed equal to 0. So that means kinetic energy is equal to 0 at the beginning. So here you also see the kinetic energy is equal to 0. When we push, okay, when we apply the force, now it gains speed. So here you see it gains speed is increasing, right? So here you see, okay, let's move. So here you see that, right? As it is going toward the right, the speed is increasing, and then kinetic energy also increasing. And that's because the definition of kinetic energy is half mv square. Because v is increasing, the velocity or the speed is increasing, kinetic energy is increasing, and this bar is also increasing. Okay, and then now this is actually equal to 702. So this is this, and this is 0. So final minus initial is change in kinetic energy. So this is equal to 702, and then you see the work done is also 702. So it proves that uh, you know uh, it proves this equation, right? The equation in the bottom. Okay, so this is the equation. So net work done is equal to change in kinetic energy. All right. Yeah, basically the same thing I showed in the simulation. Okay, so when you apply some force here, okay, you do some work, okay, And because of this work, the kinetic energy changes. And the idea for work energy principle is the net work done is equal to change in kinetic energy. Okay. All right. So here I derive mathematically from the kinematics equation. Okay. If you want to go through, you can go through. But I mean, we basically need this equation. Okay. Now here I want to say something interpreting this equation. Okay. So you know that, as I already mentioned, the work done can be positive, negative, and zero, right? So when you do positive work, this is positive. So this positive means left hand side is also positive, right? So when left hand side is positive, that means it says that kinetic energy is positive. I mean, the change in kinetic energy is positive. So when delta K is positive, that means kinetic energy is gained by the object. When kinetic energy is gained, that means it gain also the speed. Okay, and we already see in the simulation. Negative work done is opposite. So when negative work, so if this is negative, this is negative. And this negative means kinetic energy decreases. Kinetic energy decreases means the speed decreases. Okay, and then zero network. Zero network means, you know, that if this is zero, this is also zero. So that means the kinetic energy does not change. It stays the same. If initially, if it is, let's say, 100 joule, finally it should be 100 joule. It does not mean the kinetic energy is equal to zero. It, if net work done is equal to zero, it says that delta KE is equal to zero. Okay? And delta K is equal to 0 means no change in kinetic energy. Okay, it stays the same. So I'm going to stop here. In next class, I'm going to start from, yeah, this point. Okay, from the work energy principle. W net is equal to delta KE. So don't forget to watch it. Okay, all right.